तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
In the last lecture we introduced the concept of storage or a memory element which is needed for sequential circuits, because in a sequential circuit the output is determined not only by the present set of inputs but also by the past outputs of the circuit. And naturally we need a memory, we need storage elements in order to remember the output of the previous, in order to remember the previous outputs and feed it as additional inputs to the system. And the circuit we saw was a simple latch where a 1 bit can be stored, that is all we need anyway. In digital systems we only use bits, and as long as you have a circuit to store a bit of information, so 0 or a 1, you can replicate it and use it as many times as you want. Today we will see some improvements on that basic latch, it was called. First thing we will have to make is to introduce what is known as a clock. So, a clocked latch is also called a flip flop. You see, when there is a set of inputs you apply to the circuit to store 0 or 1, because we said an RS flip flop or SR flip flop, you have to give a 0 1 combination in order to store a 1 or a 0. So, you need to apply these inputs, the pair of inputs, in order to store the bit that you want. When it changes, the output changes. But then when a circuit is working in a overall system, you can't afford to change the inputs very frequently. The system has to settle down. Once you store that information, it will be recalled only when it is needed by the subsequent circuitry to the circuit which uses this. If in the meantime the input changes, what you had originally put would have changed. So, in other words, we want a control of determining when to store the information. If you leave the circuit as it is, any changes in the input will naturally change the output. Sometimes it may be intentional, sometimes it may not be intentional. So, we want to have a control of this is the information I have stored, I will keep it for a while, and when I need it I will use it, then I will go and change the input to another value which will be used in a subsequent transaction. That means I need to control the storage mechanism. This control is called the clock. So that means it is not enough if you apply the inputs. The inputs will be recognized and saved or stored in the latch as a 1 or a 0 only if the inputs are present and you also apply an enabling input or a gating input, or they call it, or a clock input. So in other words, what I am saying is, if you take that simple NAND latch, this is one of the circuits, we saw two circuits in the last lecture. One of them is this, where this is a set input and a reset input. Of course, in this case, if this set is 0 and R is 1, when set is 0 and R is reset is 1, Q is 1. When set is 1 and reset is 0, Q is 0. We did not want it, actually the set reset should have been, when set is 1 and R is 0, output should be 0. I mean, when set is 1 and R is 0, when set is 1 and reset is 0, we want the output to be 1. Set is 0 and reset is 1, we want the output to be reset to 0. But that is okay, I could have used an OR gate combination, or I can redesignate it as S bar, R bar, or whatever I said yesterday about that in the last lecture. But that is not the point here. The point here is, I do not want any change in the S and R to affect this storage mechanism. There is a bit stored here, is a 0 and a 1. When you remove the input, the bit remains stored, but that I want to be effective by a control mechanism I want to incorporate. That control mechanism is a gating signal. Only when the gating signal is enabled or the gating signal is high, whatever the S and R combination, the output will change accordingly. If the gating mechanism signal is not enabled, whatever inputs you give the whatever values you give to the inputs, it does not affect what is already stored, it will remain as a memory state. So what I can do is simply to put a very simple way of doing it is to put an AND gate in each of these, and instead of giving S and R here, I can give S and R here, these two places, and if you want to call this then S star R star is a gated output, and the second input to this will come from a circuit from an input from a signal which is called a clock signal. If clock is high, SR get reflected here, S bar, S star is same as S, R star is same as R. If clock is 0, S star and R star are both 0, right? We do not want that. We want this to work only with the gating possibility, and I can also remove that combination of that S bar R bar thing by putting instead of an AND gate an NAND gate. If I put a NAND gate here, there is a natural inversion because of the NAND gate. So now it becomes a true SR latch. That means now this would be, the truth table of this would be clock S R Q Q bar. If clock is 1 or high, clock is 0 or disabled, whatever be the value of S R and R, because it is going to remain in the 1 state, right? In a NAND gate, you put a 0, one of them is a 0, the output is a 1, right? So, the 1 state is a memory state, is it not? For this latch, 1 state is a memory state. So, this becomes memory state. That means your S and R inputs, set and reset inputs will not affect the storage the latch. The latch continues to store what it had earlier. If you want to put a new value and store it, first thing I have to do is to enable that clock signal by making clock is equal to 1. Then in this case S0 or 1 becomes 0, and not permitted or not used. This is the SR latch. I can even put 0 0. I forgot to add this. Maybe I should. I can add one more row here. It's a bit crowded, but you know what I mean. Both are 0. Memory state. This is the normal operation of the SR flip latch. 0 0 is memory state, 0 1 is a reset state, 1 0 is a set state, 1 1 is a not used state, all if clock is 1, all if clock signal is enable signal is 1. If on the other hand the clock signal is 0 or absent, is not present, whatever value you try to put in the S and R is not going to affect the outputs. Output are going to remain as it was earlier, which is called the memory state. So, this clocking is a gating signal or an enabling signal which lets you decide when to put a new value of the input and store it in the latch. After putting it and you do not want the change value at all for a while, you want to keep it for a while and then use it later on, all you have to do is to disable this gate or make this clock 0, and then it will continue to be stored as it was, and any changes in the input accidentally happening or intentionally will not affect the storage. Why do we need this clocking operation? As I said first, this may be the output of a latch may be input to the next circuit, subsequent circuit, and this any change, any frequent change sometimes unintentional will not go through a chain reaction and go to the next state. Normally in a sequential circuit we have several things happening and there must be some control or some timing or clocking mechanism as they call it, a timing precisely at which point in time everything will change. There may be several stages of this circuit and each of the stage will have to take the input from the previous stage and process it and give an output to the next stage. They cannot work at random. If you work at random, it may not, some of them may work faster than the others, some of them may take a previous output from the previous stage and process it even before the present output is available. So, but you try to synchronize the operation of all the subsystems or circuits within the sequential system, then you have a control over how to transmit data through a chain of these circuits or subsystems. So, in other words, you sort of sequence the operation the way you want. Since it is a sequence circuit, we want some sort of a control, clocking, timing. Timing has to be controlled by you. You may want it faster, I can do it very, very fast. Nobody said I should not do it very fast. This clocking can be removed and put very, very fast. If I want to work at a very high speed, I can give a very high clock signal. If you want to work very with low speed, very low speed, I can give a clocking signal which is very low frequency. So, that is possible, and that is why it is called a clock, because it sort of times the whole thing, precisely controls, like our clocks, we know when to do what, right. Unless a time arrives, not all people are, so the class starts at 4, I will have to have a clock at 4 o'clock, the class will start, because so that if people come earlier, have to, of course people come late. at least the people come earlier, I start the class as soon as somebody comes, and then the people keep walking. Some sort of regularity is put into the behavior, which helps in the overall system performance, in determining system performance. What is a clock? A clock is nothing but a signal which goes from high to low. All I want is a clock to be high or a clock to be 0. So, clock signal is nothing but a signal. If you write in terms of the time, if you draw the clock signal as a function of time, it is a signal which goes from 0 to 1 to 0 to 1, whatever is the value of 0 and 1 defined in your hardware. As I said, one general case is 0 volts and 5 volts, or 0 volts and 3.3 volts. So, I will simply put 0 and 1. I will not even venture to write the values, because it depends on the logic levels we are working with. 0 state and 1 state. 0 is the clock off, 1 is the clock on, clock low, clock high. So, the latch will work only when the clock is high. So, the best behavior is of the latch can be achieved if you make the inputs available before the clock becomes 1. When the clock is still 0, you make the inputs, then let the clock take the high value, so that the input will be transmitted into the latch, proper value will be stored, and do not make any change in the input during the period of the clock active high. When the clock is high, if you make changes in the input, that will reflect the output. I do not want that. I do not want more than one change in one clock period. I do not want more than one change in the output, because the next circuit does not know how frequently should it expect a change. I am feeding this output to the next circuit, and this circuit assumes that once in a clock cycle it is going to change. So, I will take that into account and process it and spend it further. Now, as I was doing it and processing the previous value, suddenly the value changes again, there is no reliability of this performance. I always say reliability is more important. So, if you do not know how it is going to change and when it is going to change, you can never design a reliable circuit or a circuit which works properly. So, the best way would be to make any changes into the input, when the clock is low. So, when the clock becomes high, the values gets absorbed or stored in the latch, they remain in the latch for use in the next circuit or subsequent stages, and during that clock high you never try to change the input, and again when the clock goes low, if you want you can change the input one more time. If you want to have a reason to change the input, do it at that time. This is generally a good practice in any digital system design, in sequence circuit design. It is a good practice not to make changes in the input when the clock is high, because when the clock is high it can immediately affect the output, whereas when the clock is low it will wait for the next clock pulse, only then it will affect the output. And how fast can you do it depends on the mechanism by which you can generate this pulse train, and how fast do I want to do it depends on how fast I want the circuit to work. It is a very slow process, there is no need to make it very fast unnecessarily. If the processor is very fast, it has to be done very fast. So, the speed of the clock is not the issue here. Of course, there are other considerations. What is the minimum value that the clock can take, and what is the maximum value that the clock can take? The maximum value the clock can take is the amount of delay that is required for the latch to process your input change. If I try to make a clock, if I try to put an input into the latch before it can process and put it at the output, if I try to change it one more time, it is not going to be good. Again it is going to lead to uncertainty in the output. So, the minimum minimum period for which you allow the clock to remain high is the period for which it requires, the output requires, the latch requires to process the inputs. So, the propagation delay, we talked about the propagation delay. The propagation delay of the flip flop is the time at which time it requires for it to process. So, if you try to change your clock too frequently, too fast, and change the input also accordingly, then it will get confused. So, that is the highest speed I can work with. Lowest speed there is no limit. Of course, there are some technological limitations, I am not getting into those details now. there are some technology limitations in the lower frequency speed, but it can operate it as low as possible, as low as we require normally, generally, without taking into those extra technological reasons which are beyond the scope of this course. So, such a clocked latch is also called a flip flop. The name given to this is called a flip flop, and incidentally we have removed the stigma of 1 1 being the memory state and 0 0 being the unreliable state and 0 1 being the set state and 1 0 being the reset state. Now, we want 0 1 to be reset state and 1 0 to be set state, 0 0 to be memory state and 1 1 to be not used state. That has come because of this NAND gate here in the input. If I put an AND gate, it will still be the original thing. Since I put a NAND gate, I have taken care of that problem. So, this is a clocked SR latch, also called a flip flop, SR flip flop. Why is it called flip flop? Because the output changes from 1 to 0, 0 to 1 all the time. Only 2 states, like a swing, seesaw. Is it this way or this way? Flip flop. Now, this is the basic building block, is not a latch. That means it is a clocked latch or a flip flop. That is the basic storage element, because I want a clock to control when to put the data in and when to change it. So, once you have this latch, now let us look at the other problem, 2 more problems. I said the data variation is 1. The second thing is, in order to put a 1 into this, I need to put a 1 0, S equal to 1 R equal to 0. If you want to put a 0 into this, I have to put a 0 and 1. And someone asked me, can I make it both at the same time? Yes and R. It is better to do one at a time. Depend on the clocking, the circuitry, no. But the problem in this case is, since the clock is going to be controlling the whole very operation, the clock is going to be the time at which the circuit is going to start working. It does not matter when you put S, when you put R, as long as both are before the clock becomes high. Now, still I don't know, it is very inconvenient to store a bit of 1, I need to put a 1 and a 0, store a bit of 0, I need to put a 0 and a 1. I can easily remove this problem by making one of them always complement of the other. S and R are always complement of the other, because I want to put a 1 and a 0, right. So, if I make a simple modification to this SR, so I will now use this as SR flip flop instead of redrawing the whole circuit. When I say SR flip flop, I mean this block. Which has an S input, R input, clock input, key output, now if I now connect a latch, an inverter to this, such that R is always complement of S. So, I can either have a 0 1 as the input or 1 0 the input. So, not if S is equal to 1, R becomes 0, so Q is 1, Q bar is equal to 0. S is equal to 0, R is equal to 1, will make Q is equal to 0, Q bar is equal to 1. So, if I want to set the flip flop, I put 1 in this, 1 here sets the flip flop, 0 here resets the flip flop. Earlier I could not have done it without the clock, because the clock is now required. Now I can use the clock for memory operation. For a memory operation, memory state, earlier we had to put a 0 0 for memory. Once I put an input 1 0, then remove it and put 0 0 for memory, or put a 0 1 and remove it, put 0 0 for memory. Now there is no need to put a separate 0 0 for memory. If you give a clock, the input gets stored. If you remove the clock, the input remains stored. To store the input, I give the input and enable the clock. To keep it, all I have to do is to remove the clock, make the clock low. So, I put the value and keep it for the one clock cycle. Next clock cycle, if I want the same value, put again the same value. If I want a different value, put a different value. So, this is a simple flip flop where I have removed the condition of S is equal to 1, the 2 inputs to be required, 2 inputs being required to store a bit, 1 bit of information. So, this need not be then called SR. What is the need for calling SR? Because they are always going to be. I can as well call it a D flip flop, D for data. It stores a data bit, a bit of data is 0 or a 1. So, my D flip flop is nothing but a simple input called D and a clock Q and Q bar. D flip flop. That means I have pushed this, inside this is an S and an inverter and R, all that I am not showing. What is shown here is this. The same with this. I push that inverter inside the circuit, then it becomes a 1 bar. Incidentally, we do not have to worry about the condition of S and R being 1, because of the inversion, it is never possible to make S is equal to 1, R is equal to 1, right. So, I do not have to worry about the non-permitted condition at all. It is a very frequently used flip flop. Data storage is always mostly done in using D flip flop. Now, all you need to put is data and store it. Put a data and clock it, it will get stored. Remove the clock, it stays. You want to read it, that can always read it any time, because even without the clock the Q remains 1. But if you want to change the data, I need to put the clock again, put the new value of the data. So, D flip flop is a very simple 1 bit storage, which is most frequently used for data storage. When you say memory, for example, in computer or calculator, any circuit, it consists of all minor defined. Of course, the memory is a huge memory these days, but individually, finally, as I said, whatever is the size of a memory, finally it is the bits to be stored, and bits are stored in a D flip flop. So, D flip flop is very often used, very frequently used as a data storage device or circuit. That is why it is called a D flip flop, D for data. So, we have an SR latch converted to SR flip flop by introducing a clocking. I told you the reason for clocking, and I said what is the need for 2 inputs when the clock is there to control. I can as well have only one input called D input and make the other input complement of the other, and you got a D flip flop. So, I can put a data, store it and read it anytime. When I want to change the data, I put the clock again and save it. But when you look back at this SR flip flop, there is some attraction in that. There are 2 inputs. So, we had 4 combinations: memory state, 0 1 state, 1 0 state output, I mean, and then the not used state. There is a circuit in which something is not used. If that can be used also usefully, if I can remove that not permitted stigma attached to the SR flip flop, and 1 1 also can be made as a useful input in which some activity can be achieved, some functionality can be achieved, it will be even better. So, D flip flop is okay for storing data, but I want to now look at the SR flip flop one more time. What is that we can do in order to remove that stigma attached to SR being 1 1. So, let us revisit SR flip flop. I will have to, in this case, since I have to explain the operation, I am putting this gate circuit again. Otherwise, when I say SR and put a box, you know what is inside. When I say D and put a box, you know what is inside. So, in this case, since I have to explain the functionality, I am putting the circuit again using gates. we call this clock. If you remember, we wanted it as S or, and we know how it works. Just now saw a while ago how the circuit works as a SR flip flop, provided you make sure that 1 1 S1 S equal 1 or S equal to 1 condition is not encountered. It will work as a normal flip flop, storing 1 if you put S is equal to 1 or is equal to 0, storing 0 when you put S equal to 0 or is equal to 1, and put 0 0, it will store whatever, it will keep whatever you have stored. Now the clock is an extra thing, with the clock only it works, without clock again it remains storage. So there are two ways in which you can keep what you have. One way is to remove the clock. When there is no clock, clock is low. When you say remove the clock, don't physically disconnect the wire, I mean clock 0, clock is not there, on, clock is off. Or when put 0 0, even when the clock is high, when you put out input 0 0, still it will stay in the memory state. Now I am trying to make this into a 3 input NAND gate. I am going to connect the output of this into this, I mean this input to this output and this input to, let us see what happens with this change. I have taken the SR flip flop, replace the input NAND gates by 2 input NAND gates by 3 input NAND gates and the input the first stage, second stage remains as it is. So 0 1 1 0 1 etc. Now let us say we are looking at clock high, clock low of course it remains in memory state, no problem. So we will only worry about when clock is high. When clock is high or clock is 1, let us assume now S is equal to 1 or is equal to 0. When S is equal to 1 or is equal to 0, clock is high, the output is going to, without this third input of the third input of the NAND gate, Q would be 1 and Q bar will be 0, correct? And when clock is 1, S is equal to 0, R is equal to 1, again Q becomes 0. So this is normal. I am trying to say that this is same as the previous thing, no problem. So 0 0 state, clock 0 state or 0 0 state, they work as memory states. S is equal to R is equal to 0 also works as a set operation. S is equal to 0 or is equal to 1 works as reset operation, no problem until all. The only one condition which has not been dealt with, the SR flip flop, we will now look at it, that is when clock is high, S is equal to 1 and R is equal to 1. We will try to venture this inputs combination, we will try to put this input combination, see what happens. Now clock is 1, S is equal to 1, one of them is high and other one is low to start with, let us assume. So let us assume that to start with this was 1. So let us assume initially this is 1 and this is 0, we will put this here, this is 1, this is 0. So this 0 is here, this 1 is here. Now we put clock is high, R is high, so all the 3 inputs are high for this. Here 0 0 1, is that right? S is S is gone 0 1 1, 0 1 1 is the input here, this is 1, this is 1. So I am making clock high, S is high, R is high. I am connecting back the output Q bar into this gate, output Q into this gate. The 0 gets reflected here, 1 gets reflected here, 1 1 1 is the input of the NAND gate. What is the output? 1 1 input gives you 0. and 1 1 0 1. Okay. And 1 0 at this stage, what is the output? 0 1. So when you give 1 0, this 1 gets changed into 0, this 0 gets changed into 1. Do you understand it? I am putting an extra input to the two input NAND gates, keeping S is equal to 1, R is equal to 1, keeping clock high, and I am connecting simply Q back to the first R, the gate, this gate, Q bar back to this gate, and I am now analyzing the performance. We have to arbitrarily assume, I can assume that first to start with this was 0, this was 1, I have to start somewhere in the analysis. So I just assume this way that Q is 1 and Q bar is 0, this 1 gets reflected here, 1 1 1 gets an output 0, 0 1 1 gets an output 1. So 1 0 at the input of the NAND gate, original SR latch, remember the NAND gate 1 1 was a 1 0 was a reset state, 1 0 is a reset state, so just 0 1. Now this 0 gets back into this, changing this 1 from to 0, this 1 changes the 0 to 1. Now this input of the, this NAND gate will have 1 1 1 input, this NAND gate will have 1 1 0 input. So the output of this NAND gate will become 0, output of this NAND gate become 1. When this 0 1 combination applied to this back to back latch, back to back NAND gates, the output would be 1 0. You get the drift. What I am trying to say is, because it is a self, there is a feedback, as long as I keep the clock high and as long as I keep my S is equal to 1, R is equal to 1, all inputs to the NAND gates are frozen except the ones which are coming back, feedback inputs. Those inputs were 0 1 to start with. So when I put 0 1, this was 0, this was 1, the output was 1 and this is 0, that 1 0 changed the output from 1 0 to 0 1, the 0 1 got fed back, made the inputs here 0 1, which made the output 1 0. I can go on repeating this. So if I now get this 1 back, this becomes 1, this becomes 0, this makes it 1, this makes it 0, so 1 0 here makes it 0 1, keeps going. As long as I keep my clock high and as long as I keep my R is equal to 1, S is equal to 1, Q changes from 0 to 1 to 0 to 1 to 0 to 1, Q bar changes from 1 to 0, 1 to 0, 1 to 0. Of course, I am assuming clock is high, S is equal to 0, S is equal to R is equal to 1, clock is 1. A forbidden state of S is equal to 1, R is equal to 1 has been now converted into a state in which the output keeps changing all the time. This very constant change of inputs, change of outputs, this is called toggling. This is a toggle action. This Q and Q bar changing uncontrollably, if you will. If you want to call it uncontrollably. As long as I keep my, the only way to stop doing this is to remove the, make the clock 0 or make changes in S and R. With S is equal to, when S and R in the other 3 combinations 0 0 0 1 1 0, no problem, it behaves exactly like an SR flip flop. Moment you put a 1 1, in the previous case it becomes an operation which is not predictable. In the SR case, yesterday we analyzed that. Whereas now we can say that it is predictable but useless. Output keeps changing from 0 to 1, 0 to 1, 0 to 1, all the time keeps changing. But it may be useful sometimes, it keeps changing all the time. This changing constantly is called a toggling operation. In fact, it is so much changing so uncontrollably that they call it raising, it raises. Toggle is only changing from 1 to 0, 0 to 1, just like a seesaw as I said. If 1 becomes 0 and 0 becomes 1, that operation is called toggle. Actually, strictly speaking, it is not a toggle, it is a racing, it is a race, keeps something like an oscillation, output keeps changing from 0 to 1, 0 to 1 to 0 to 1 to 0 to 1 and 1, in the other case it is a complementary operation. So, if we want to draw the waveform for this, output of flip flop with S is equal to 1, R is equal to 1, clock is equal to 1. Under that condition, I am drawing the waveform for Q. When the clock is 0, there is no problem, output remains, let us say 0, it could be 1. It is a memory state, we do not know it is a 0 or a 1, we will have to assume something. So, 0, but then it becomes 1, it becomes 0, 1. And then again it will remain calm down. When the clock is 0, it calms down. Again when the clock goes high, it goes berserk. You get the idea, I do not have to keep on doing it. So, between state 0 and state 1, it keeps changing all the time. When the clock is high, it remains as before. You see, if it is a 0, it will remain 0, it is 1, it is not necessary it has to remain 0, it can remain 1 also. And the Q bar is a complement of that, I do not want to draw that, Q bar is a complement of that. This behavior called race. Toggle is a mechanism by which the output changes from 1, output becomes 0, 0 becomes 1 constantly, but in a controlled way. It is an uncontrolled way. This is a toggle. The difference between toggle and race is uncontrolled, toggle is controlled. When you want it, it changes back and forth all the time. If you can control this phenomenon, we can use it. Whenever you want an output to keep changing, we can use this, and we will see where we can use this later on. But you can take it from me now that if you can control it so that it can only change once in a clock cycle. This will be more useful if this clock cycle is 0, next clock cycle is 1, then it becomes 0, then becomes 1, then becomes 0, 1, 0, 1. If it changes, this pattern is interesting. I would like to have this pattern, but not as frequently as like this, but once every clock period or once every half clock period. When the clock is not there, it will become 0 and the clock is 1, something like that. So, more controlled, where I can predict the behavior. I said anything which is not predictable is not useful in any practical circuit. I cannot have a circuit in which I can't design a circuit and sell it to a customer and say, you try your luck, it may work for you. Would you like to sell something like that, or would you like to buy something like that? No. That is why I do not want this. This racing has to be avoided. But now let us see how fast can it change. What determines the speed at which it changes? Somebody said something? The propagation delay from here to here. Moment I make this change in the input, it takes a couple of clock periods, I mean the gate delays to go to the output. So, the propagation delay of the flip flop determines the duration for which the output can remain constant, after that it has to change. So, the speed at which it will change will depend on the propagation delay of the gates. Whether it is too small for us, 1 nanosecond, let us say couple of nanoseconds for this gate, another 2 nanoseconds for this, 2 to 3, let us say 2 to 3 nanoseconds per gate, a total of 5 nanoseconds let us say. Every 5 nanoseconds the output changes from 1 to 0, I can't do much with this, right. So, I would like to have it change but at a more orderly manner, more regulated intervals. There are two things you can do. If I make a clock even smaller than this propagation delay, I can make it only change once in a clock period. Is that not? Suppose I give my clock, I said as long as the clock is high, this is going to keep changing, keep going raising. When the clock settles down to 0, it will remain whatever is the last value, it will remain. Again when the clock goes high, it goes berserk. I told you like that. So if I make the clock period as a theoretically in a clock period or clock on time, not even period, clock on time is less than if then racing can be avoided. Is it practical? Can I have a clock which is working at? Of course, if it is necessary I have to do it, but not for everything. For example, with a counter I want to count people in coming into the room. I want to have a very slow clock. Many events are very slow. Do not always think of Pentium 4 which works at 2 gigahertz. Even there is lots of things inside which are very, very slow. Do not get carried away with the speed with the salesperson tells you. At what operation, what can you do at 2 gigahertz per second? I cannot really. Can you read something at that speed? No. Can you input something at this speed? No. So all this is a misnomer. And of course, there is something which works inside which is 2 gigahertz per second. I mean, but that is not what we really want for interfacing. So this is not a practical condition. If I make my clock period very, very narrow, it will be less than this. If I make it less than this and go back to 0, if I can generate a clock like that and use it for my flip flop, then I can have a condition when the clock is 0, it will remain constant, the clock is 1, it becomes 1, and again back and forth it will go. That is not a realistic condition. Other condition is somehow make the change possible only once in a clock period. That is what I mean by toggling operation. I would like the change of output from the present state to the complementary state. If the output is 0, I want it to be 1, output is 1, I want it to be 0. So one thing, this is one possibility. Second possibility, if flip flop is made to toggle, that is why I will now use the word toggle instead of race. Because toggle is a useful operation where it changes from 1 to 0, 0 to 1 in a controlled way. Toggle only once in a clock period. However large this clock period is, however long this clock period is, whether it is milliseconds, microseconds, nanoseconds, seconds. When I have with one input, one clock period pulse, I will only have this change once, not again. This will be useful. So this flip flop may be useful. We will have to see how to do that. So what we have to see is, this is not possible, impossible condition to meet. How to prevent this toggling racing and make it toggle. In that case I have one extra feature of my SR flip flop. SR flip flop will work as it is. There is no problem with other than 1-1 condition, no problem. It is a good flip flop. It is not a bad flip flop as I am saying, making it. I am not making. Don't think it is a bad flip flop. It is a good flip flop. That means it has 0-0 state. With clock 0, it behaves as a memory. With 0-0, it behaves like a memory. With 0-1, it is reset. 1-0, it sets. These three features are common. That 1-1 condition is a rogue condition which was not there. I am trying to tame it. In that process, I have got a beast, which is race. I have to remove that beast operation, make it a useful operation. How to do that, we will see in the next lecture.